is a little chatbot that I've built. Okay, and at the end of the presentation, I will take you through how I did it. But before we go through, I've the chatbot. What the chatbot is essentially doing, think of it as ChatGPT reading through data. So this chatbot that I've built is reading through my data, and my data is an income statement of my business, of of my business, which has been running for about, I think, 20 years now. And so it's an income statement, and I'll just like two volunteers to ask it question. Just give me a question and I'll type it, and yeah, we'll see what it says. So for example, ask what the profit is or what are we selling or something. Are there any volunteers? All right, Tavo, please could you ask me a question that I can ask this?
What is, it does give you ratios, right? So what is the profit to loss ratio
What is, I don't know, I've never checked that, but let's see what it says. What is the profit to ratio?
to
Profit to
loss?
ratio. Yes. Okay. So to calculate profit to loss ratio, we need to know the net income for both years to calculate this. So this is my profit, this is my loss, and that's the profit and ratio. So therefore, the profit to loss ratio for 2003 for my business was 13.57%, and 2004 was 15.91%. All right, Nomsa, would you think? Taba, you said, how do you feel about the answer?
I'm quite satisfied because it gave me how to calculate and not just the answer itself.
All right, great. Nomsa, do you have a question we can ask the chatbot?
Can it be any question?
I mean, it has to be in context of an income statement of my
Okay.
business. So you're basically asking me questions about my business and money.
All right. What is the company's current loss versus last year's loss?
Okay, so we've got 2004 and 2003. No, but is it a loss or is it a profit? We don't know. So maybe,
We're trying to compare how much we've lost between the years, like in percentage wise.
okay, maybe have we lost profit in 2004 and 2003? No, we did not experience a loss in profit between 2004 and 2003. The net income increased from 33 to 41,000. All right, so this is, I guess I was just doing this to get a little bit of engagement of what I'm trying to speak about, but is how to build a large language model. So how to build something that I built, what I just demonstrated in the beginning there. It's just really going to be high level and the foundations of a basic structure. That if you were to know how to build this, you'd know that obviously I've left out quite a bit, but it's just for everyone to understand. Could someone please confirm if they can see the presentation and if it's
I
full
can
screen?
see
Is it full
full
screen?
screen. Yes.
All right, perfect. Okay, so large. So we need to first talk about a generative AI first before we speak about large language models. And generative AI is a field under machine learning where its models learn various abilities by finding statistical patterns in large data sets of language originally created by humans. Okay, so these models, These models are called large language models, and we've got foundational models. I'm sure everyone here has used ChatGPT. We've got Bloom, for example. That's if you know finance publisher Bloomberg, they've got their own called Bloom, and then Flan T5, which is just another basic model. So that's in a nutshell what large language models do. Be showcasing in my presentation is how the models work, some prompt engineering, how to create text outputs, how to fine tune. I'll do this briefly, and also how to deploy. And this will be at the end, how I created that model that I just presented in the beginning. Okay, so how large language models work. I will be referring to ChatGPT because I think it'll be relatable. So in sense, what you do is, as an individual, a person puts in a prompt, which is in the form of a text, because that's how these models interact. And then this text then processes that the model then processes that text that you've put in, and it gives you a response. This response is coded completion. And if the model has processed the data well, if it knows Joburg's geography, it'll be like Santon it'll give you that response. And that whole process from beginning to start is called an inference. So you go to chatgpt.com, you put in Python, how do I import CSV? It does it, and then it gives you a response, something like that. Okay. All right. And then these models, depending on the level that you've interacted with the models, but they can do far beyond just give you texts. All right. So they can, if you ask a large language model to write you an essay, it will do so. You can give it parameters, should be 500 words. They can translate. All right. So they can translate isiZulu to English, depending if the model has been trained on isiZulu and English. And they can also, I'm sure because we're a tech company, I'm sure all of us have come across times when we're facing trouble with some script and we just put it through ChatGPT and it helps us find the error or to write the script. But all of these use cases are dependent on what model it is, on the model itself, right? So we've got models like BERT, Flanty5, GPT, and Bloom, like I mentioned earlier. But you would see that the bigger that the model is, such as ChatGPT or GPT, large language model, it can process all of these items here, right? Because it's been trained over billions and billions of data. But you've got this model called Flanty5, which is slightly smaller, and it's been trained on like conversation. So if you were to ask this model how to code Python script, it might not be so familiar, right? And also, some models are better doing other things than others. So Bloom will probably give you a better finance response than ChatGPT would. Not to say ChatGPT won't give you a great response, but Bloom is being trained on primarily finance data. And just another thing, when you're making your own models, it doesn't necessarily mean that a model has to be big to do great things. I'm sure you've seen some flaws of ChatGPT sometimes, where a BERT model can do well. Maybe a BERT model has just been made to translate isiZulu to Xhosa, and it will do a much better job than GPT would. So large language models have been around for a very long time. And in the next slide, I will speak about the challenges that they used to face. But you can imagine a computer, just think of a basic computer trying to break down what bank is. Sometimes we all know the famous saying, my English data bundles have depleted, because English English and language is not as straightforward as mathematics is. So, you could say I took money to the bank, but the computer doesn't know, did you take money to FNB or did you take money to, to the Limpopo Riverbank, right? Or the teacher is teaching, the teacher is teaching a student Python. Is it talking about a reptile? Whose laptop is it? There's not a lot of context. So before GPT came about, like I said earlier, these models have been there, but they haven't been so great. And the reason being because RNN, recurrent neural network, this was what was there, but it wasn't so great at knowing the relationships between words in a sequence. So you could give it maybe my tea taste, all right, but it wasn't so great at relating that my tea tastes with that the milk is bad. So meaning you can't predict that the next word is going to be great. And that's really when these large language models became very popular. I think if you can think of like a chatbot 5 to 7 years ago, it was not so great. I personally don't like using chatbots because I've had bad experiences with them. But recently I used a chatbot on Spotify and I was impressed that it worked really well. And because back in the day, they used to use very poor backed models. So now what we have is we've got transformers. All right, so transformers, don't mind my little art here. I couldn't find a clever way of doing a map. But what we have here is an attention map. So what transformers can do, transformers have the ability to create a relationship between each word and other words and find the relevance of each word within that sequence of a sentence. And also creating some sort of context to what exactly this sentence is saying. So yeah, so this is an attention map, and this is what transformers do, and this is what previous RNNs couldn't do. They would just, Python with the laptop, but they wouldn't know if a teacher or a dog or someone taught a student Python with the laptop. So I'm going to be just showing you guys how the transformers work, right? And this is a really detailed diagram of how transformers work. But how they essentially work is, they pay a lot of attention to each sequence, each word in the sequence. And Google has a nice word saying, attention is all you need. And how these transformers work is, we'll go through it step by step, but inputs go in just like any model. A couple of steps happen, and then, they come out. So let's say we've got a sentence. So this is, oh, I just missed step one. So I think the most important thing that I should put across is large language models don't process language. They process numbers. And this is important because this is how we find relationships. We can create relationships with numbers rather than words. So here we've got the teacher taught, and these words are tokenized. So tokenizing is a method of changing a word into a word into a number. And there's many tokenizing methods. You could even break down teacher to T and ch, and that could be a token ID. And the reason we do that is in step 2. So after this is the first step. So think of it when you put in a prompt. So I think how I'd like you guys to see this is when you put in a prompt into ChatGPT. And in fact, no, let's not think of it like that. When we're training a model, it's because we're actually talking about building a model. So when I'm training a model, for example, that one that I just showed you of reading my income statement, all right, it needs to process those words in that income statement, and then it creates a dictionary. And in that dictionary is numbers from that range from 1 to 100. Let's say in the income statement is 100 words, and it finds a relationship between these numbers. But I should also mention the reason why it was easier for me to create this model is, as you'll see soon, is because I've relied on GPT's model, large language model, so that I don't have to train for long and I could prepare for this presentation. So GPT's got like trillions of words. So when Tabo asks those questions, right, those words will go through into GPT, and this is what then happens, right? So the reason we then create, the next step after tokenizing the words is we want to embed the words, and this is where the relationship comes. So the words are then mapped to vectors, and we do vectors because that's how we can create a relationship in a space. So think of it as I've demonstrated over here. We'll have internet, student, book, and computer in this 3D vector here. And when you make the prompt, when you put in the prompt, it will then say, okay, so Tabo is asking about the income statement and profit. It'll come and it'll find words where profit, so for example, student and book are closer than student and fire. Right? So when we're now giving a response, student and book are likely going to come out in the response than student and fire coming together. So that's why we tokenize, and then we map these tokens into a vector so that we create a relationship. We get context of what the sentence, that what the sequence is trying to say. Right? If a teacher is teaching a student Python, it's very unlikely there's going to be fire. Hence, fire and fox and student are further away in that space. So in this embedding space here, it's really, it's like building a house and food is in the kitchen while the toilet is far away from the kitchen. What the others are not going, they won't be closer to each other. You know, that's a wild example, but yeah. So and like I was mentioning earlier, that's how you then create the relationship, right? The distance between student and book is much closer than the distance between student and fox or student and fire. So when we're now predicting what next word to give Tabo in his response or Nomsa in his response, we know that student and book are likely going to be together. And if we get fire, then that's a very wild response. And you can prevent this from happening by fine tuning. And I'll show you in a little example fine tuning in a second of how we can ensure that the model stays to book and student. But I should also mention that we also fine tune in a way that we do want the model to be creative. We don't want it to just create relation between these three things, but which I'll show you in my example, is we want it to be creative to also sometimes consider fire or fox if it makes sense. Okay, so once you've done that, then the next step is we've got our vectors, the tokens have been put into vectors, but we also need to put them into positional embeddings as well, vectors as well. So what positioning embeddings is, we need to maintain the we want to know where each word is in a sequence. We don't want to forget where that word is in a sequence, or where it would be found in a sequence if we're to ask the model, or if we're to make a request from the model. So, you know, an adjective or a noun is going to come one after the other. This was what will help the model make those decisions as it's predicting. Step 4, what happens in the model is, what we're doing here is we're creating a relation. We're finding the context of each word within the sentence, and really what each word, what each token, what it means within the sequence, and the relevance of that token in that sequence. And before an output is given, this will have the it will find, for example, the context of Python and laptop, and Python and student, and it'll iterate over and over again and find the relevance of student and teacher, and while it's doing those iterations in this process, it's getting a very good idea of it's getting a good nuance of where each word goes and how ideally it should project these words, and where which word is likely going to come out first. What also happens here is it in this step? What also happens here, or did I forget to mention? No, it's in this step. What also happens here is we create attention weights. So each word in the sequel is given an attention weight. And this attention weight basically means, you'll see in the last step, is we're giving each word a probability of when it's likely going to be predicted, right? And what will usually what's happening in this encoder and decoder here, whilst we give each word an attention weight, we will then normalize, right? If you've done like an AI course, you see these softmax, these activation functions, and what these are essentially doing, they're normalizing. So in this step, we give a word in a sequence an attention weight. It can be any number, right? And the number is usually, the higher the number is, the higher the relationship it has to the next word that's going to be generated. But in this next final step is, we need to normalize it so that everything is between 0 to 1, so that we can then have a probability. Because you can't have a probability if you've got numbers like 1, 50, 20, but you can definitely have a probability if you've got numbers between 0 and 1. So you can create percentages. So 0.5 would be 50%. And then these words are then put into like what you're gonna call it, uh, order of which word is likely going to be predicted. The higher the probability, the higher it is closer to 1 after normalization, the higher it's likely going to be predicted next. Remember, so just remember that after this decoder and encoder, part of the transformer does an iteration of the sequence. So it iterates, predicts a word, iterates, predicts a word, iterates, predicts a word. So as it iterates, it's creating these attention weights, and is then creating the probability of what the next number is going to be. So the teacher is teaching. So this teacher taught. So taught, after you say the word teacher, taught is going to have a higher probability than any other word in the sequence, so that it's predicted next. Yeah, so that's how a transformer works. Very powerful thing. So that's a cool way of thinking, like, of what happens in the whole thing, when you put a prompt inside ChatGPT, for example. Okay, so prompt engineering is basically, it's tweaking you're tweaking your you're basically trying to tweak your large language model to give you a certain answer, right? I think, like, if, let's say, think of it in ChatGPT, right? If you say send, for example, Mrendeni is my manager, I'll be like, create me an email to request for leave. All right, it's gonna create an email. It's just gonna randomly create an email. But I'm gonna be like, but for it to create, because I really want Mrendeni to give me a leave, I'm gonna want to convince her a little bit. So I'm gonna be like, create a convincing email, create a formal convincing email brief requesting for leave to Mrendeni. And it's likely going to give me an email that Mrendeni will empathize, like, oh, okay, this guy is tired, he needs to take leave, something like that. So that's what's happening here. So you'll find that with your smaller large language models, you will need to give examples and of how you want it to return a completion. because they're not trained on a lot of data. But with larger models, you won't have to give an example, and I'll show you in the next slide. So this, for example, it will be like ChatGPT. You just ask it where is Santon located in South Africa, because GPT has been trained on millions of data. It doesn't struggle to give me a good answer, right? So, but this is where like the fine tuning comes in, when the fine tuning inside your model, and we're going to give it some context. So what we're going to do in the next slide is I'm going to show you how to give your model examples, to give your models examples so that it's in line with the type of response you're looking for. All right, so let's say I've got a smaller model. All right, so let's say I love data science, right? And because this is a smaller model, it doesn't have any example, no in context or anything. It's just going to give me a random example, right? It's going to give me very nice compute. This is not the request that I'm looking. This is not the completion that I'm looking for. So I need to give an in context. So this, when you don't give an example, when you just give GPT a question, no example, that's called zero shot inference. But let's say I give it an example so that I want it to give me a response in line with what I want. So I will give it an example. I love data scientists. This is a positive sentiment. So this is something good, right? So I give it that. And then I also tell the model, I don't like this chair. So then I ask it, so what sentiment am I asking for? So I one shot in inference, meaning I've given the model one example, and then it's now likely going to give me a proper answer. So when you're building your model, this is an example of fine tuning. I don't speak about this in my example of how I built mine, because that's a whole bunch of other work. But when you're building, let's say you've got a small model, it's reading through small bits of data, and it's got a very small. This is called a context window. So where you put your request, where you've got a context window that can take in a very small amount of words. You want it to be able to take an example so that it's likely to give you the right answer. So the client, the user, is encouraged to give an example before they put in their prompt, and the model then reads the example, and then it also gets into line of what the client or the customer or the user is trying to look for, and then gives you a completion of what you want. This is also important. Think of it, you don't want a model to be giving you not just incorrect answers, but you don't want false information. You don't want vulgar. This is another way of, maybe you could, not getting unwanted information. So that's kind of the gist of how the model works, and the small example of how fine tuning work. There's many other ways of fine tuning, but I thought this is probably the simplest one, because I think everyone talks about prompt engineering. So what are the challenges that we face with these models? All right. So you can imagine, if a model is training through billions and billions of data, it requires a lot of GPUs and memory to store the training, but also just to store for example, those weights that I told you in the past, and I told you in the previous slides, to have weights, to predict what the next word is going to be. So as a user, I think even businesses will struggle with this, because they would need to go on cloud and use a lot of this computational power. But as a user, if you want to make your own model, you need so much power, uh, which is so I think most of us, our laptops are decent laptops. So your laptop is probably a 4 GB laptop with 4 GB RAM. But now think of, for example, you've got like a billion parameters, and one parameter is 32 bit, and you multiply that and that's now 80 gigabytes of GPU RAM. I've never even heard of a single computer that's got like more than, I don't know, maybe if there's gamers in here, they can tell me if there's computers that have got gigabytes like that. But that's a lot, and that's expensive. So that's one of the holdbacks. But you can obviously there's ways to go around this. You could obviously leverage an existing model, which I did in my model, or you can, you can break that down, and you can break down the 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 storage size of a parameter, to break it down to be less accurate from 32-bit to 16-bit or 8-bit. So now you're saying 8-bit by a billion. Now, it's not, we're not talking about 80 gigabytes. We're talking about maybe something that's more practical. So that's one of the main challenges. There's other challenges that are obviously obvious, but I thought computational challenges was one I should talk about, because I think it's an interesting topic and everyone would like to get involved, but they need to be aware of these challenges. So how quantization works is essentially is, if you're going to be using 80 gigabytes of GPUs, and if someone is into hardware, maybe you can correct me, 8 gigabytes of RAM, you're going to need quite a number of GPUs. But if you break down your accuracy from 32 to 16, you need less GPUs, and that's something maybe your computer might have, or maybe a work computer with serious GPU size can have. Yeah, so let me just finish quickly so we can go to the model quickly. And then just business use. I guess this is like Patanani's favorite question, like what's the business here? But there's many ways, right? So I think there's, right now, let's say we make a model for a client, we give them a Power BI model, and they can make filters, and then in the presentation of like, we filtered for this is what your numbers are saying. But what if one not there, and after the presentation, and the client really wants to sit down and make inquiries of the data? Now they can actually have a conversation with the model, with the numbers, and get responses immediately. And if you've even got a smarter model that's augmented, so augmented basically means that your model is in touch with current data, right? So you might have seen, if you look on ChatGPT, the latest data it has is 2022, right? So it doesn't have that aspect of augmented, of that augmentation of large language models. But I'm sure maybe GPT-4 might have to current affairs, but I know GPT-3, the one that we have access to for free, has got data until 3.5. But besides that, for example, we can create a health application that gives us access to credible data. When you're sick with the flu, you start asking Google information, but you never know if it's really credible. You just assume. You look through, and sometimes you might even get a response that's telling you you're about to die. So that's the end of the presentation. But before I can just get a couple of minutes just to share a little bit of how this is made. This chatbot is, I'm leveraging off LangChain. So if you Google what LangChain is, it's a framework to assist people to build large language models. It's not a large language model, but it's a framework. So the framework, either you're building and training a large language models on new data, or you're doing what I'm doing now and you're leveraging off OpenAI. So we're using LangChain and vector stores. This is essentially, remember when I said you map you map your token IDs to vectors, and then these vectors are stored. We've also got positional embedding. We want to store these, and then there's the embeddings. You remember the positional, and you kind of do that, and then now we're kind of creating our model. I want to see what are the important things. So when you're tokenizing, before you tokenize, you want to kind of break down the data so that it's easier to tokenize. So you split the data into chunks. Somewhere here we do define the chunk size is 1,000. So we're saying break down the data in my income statement after 1,000 characters. right? And then there's what's another important one? Conversional retrieval chain. This is another important one. So this one essentially means after you've broken down my data into chunks, when you're now returning me a response, don't return me a response in chunks, right? Okay. No, actually, this is saying return the response in chunks, but we then have this is this one? No, it's this one. So this one, what was saying, don't return the response. Don't respond to Tabo in like all the information. Give Tabo the information that he wants, right? Don't give me an entire chunk. Give me the information. So this is what compresses. This compresses that information, and this allows us to upload stuff. And yeah, then we're doing a whole bunch of stuff. I'm running out of time, I know. And then yeah, and then you load, and then yeah, and then this is cool because what happens afterwards, you got like a very nice user interface thing, and then you can ask questions. The last thing I'll do before I leave, sorry guys, I know Namsa is probably about to kick me out, but this thing is really cool in the sense that you can upload information. All right, so some of you might know, I've got a very good background in pharmaceutics. So I got this from one of my textbooks. I got a piece of information about painkillers. So what I've just done here is from my textbook, I got a PDF about a few pages about teaching us about painkillers. I've uploaded into this database, right? Because up here in the code that gives me the option to upload. So now I'm gonna ask my database some questions about painkillers. This will be my last thing before I quit. But you then ask, Nay, what are some names of painkillers? Or no, analgesics, your paracetamol, etc. And let's see what it gives us. Okay, so see these are your aspirin, codeine, something like that. Your fentanyl. These are the addictive ones. And yeah, that's the end of my presentation.